Hi everyone, and today we'll be talking about V-star, basically a visual search algorithm that guides a multimodal large language model to progressively iterate over an image, narrowing down the scope and eventually answering the question. So it's quite an interesting approach because it kind of changes the inputs to the large language model in order to help it to better answer a question. So this kind of multiple iterations and refining of the context is somewhat similar to like chain of thought. You guide your thoughts towards there, or more similarly, it's like more like the React mechanism, the reasoning and acting framework, where you slowly act towards a endpoint. However, actually, it's not similar to any of these mechanisms. This V-star is actually more complex than both of the React and chain of thought, and we shall explain why in this. Firstly, before we move into V-star proper, okay, let's just see why we are looking at this paper. Okay, so in the paper, they claim that the abilities of this model is actually better than GPT-4V. Okay, that's quite a big claim, all right? And I put supposedly better because I found that GPT-4V is still better at most other cases. It's only in the specific context of this paper that they make it such that the experiments kind of favor their model. All right, so let's see what kind of experiments that they did. So for example, you have this ape over here. The ape is holding a saxophone. Okay, that's the GPT-4V's answer to this question. What is the instrument held by an ape? Right, so you can see this is the ape here. It's not a very conventional picture because there's so many stuffed toys. It's actually quite hard to find out this. But for their method, the search and tell or SEAL, right, the instrument is a guitar. So they actually dissected the instrument correctly. So how did they do this, right? So let's see what exactly did they do over here, right? So how come GPT-4V failed, but this SEAL method can work, all right? So the main thing to know, all right, is that whenever we do image processing in a large language model, all right, we need some way of encoding this image into some tokens, all right? Because as you all know, for a transformer, you do stuff like this, like my name is, so you have a token and then like a transformer predicts the next tokens. So transformer predicts next token. So in order to do multimodal large language models, we kind of need to make the image split into multiple tokens so that we can do inference over it. So the most common method used right now is to do this thing called contrastive language image pre-training. So actually, I intend to cover this in the next session. So this basically makes all input modalities, like for example, images, okay, and text. I mean, there could be other image modalities as well, like voice and so on. But all this could be put into a common space here. So I call this latent space. And what we want to do is we want to make sure that the input representations fall within the same region in the latent space. So like usually how this is done is using some contrastive learning to like pull together like the same image and the same text. We try to group them together in that latent space. So latent space is something like a space whereby similar concepts are grouped together. All right, so it's usually in a vector, like an embedding space. So this contrastive language image pre-training, these clip embeddings, help to group the image and the text into the same latent space. And the most commonly used one is actually based on this vision transformer. So before I move on, any of y'all here have heard of vision transformer? Can you all just raise a hand just so that I know that that you have heard of this before, or it's completely new?
A new for me.
Okay, so let me just go through a little bit slower. All right. So for vision encoders, what you do is like this. You have this image, right? And what you do is you split the image into like jigsaw pieces. You know, you split into small little icons. And these icons will then be fed here. All right. So one by one, you have all these tokens here. And okay, the interesting thing is they actually make this picture into an embedding space. Like for example, 0.3, 0.2, 0.5, and so on. So this set of pixels here in this top left part of the picture will become like some form of embeddings. okay, using some form of multi-layer perceptron to map the input patches. Okay, so can you all see that there's some issues with this embedding method, right? You see, you split your image into these small little squares or rectangles or whatever you split into these portions, and then you map with this embedding. And you can see that if, let's say, the image, like for example, you have a building in these two squares here. If you split into two, okay, you might not be able to make sense of the image because like one might be here and one might be here. Like you map them differently into different embeddings. It's just like, you know, when you do your text embeddings, no? If you split away like the paragraph, like for example, John is a doctor. John gave, like for example, John wrote a letter. Okay, so if let's say we split away this one, your second piece second sentence may not have the context of the first sentence. So this is also one of the issues of text embeddings. Is like if you take away the context and then you try to embed this part here, you might actually lose out the meaning of the first part. So maybe the letter here is your MC, your medical certificate. But you know, because you split into these image patches, you kind of lose out the idea of what this letter is. So similarly for this, because of the way you split the patches, you might actually lose out the things that connect the patches together. And what's worse, okay, you look at this image here. Can you see that this image contains a lot of windows and everything? Right? Can you imagine what will happen if you embed this, right, without preserving the spatial features of this? Anyone can tell me, like, what do you think will happen if you embed this patch of pixels into an embedding, but you don't tell it where the location of all these windows are? What will happen to the embedding? Anyone? Can your embedding still discern back these pictures, these locations?
You'd have no context, yeah.
Yeah, so that's the issue of the embeddings also. So the embeddings are a very crude way of representing pixels. So you lose out a lot of spatial information. So I'm quite sure a lot of leading large language models that are multimodal, they use VIT, Vision Transformers, because it's shown to be the most performant by Google. But at the same time, it also is the most performant because it's trained over the most amount of data out of all the transformer models that does image out there, right? And one thing about this way of encoding the pictures into these patches is that you lose out all the spatial information, you lose out the intricate details. And this is a key issue because like if you try out GPT-4V, okay, they did not release the architecture, but I'm quite sure that the architecture is linked to a vision transformer, right? I think the main thing you can see for GPT-4V, if you play around with it, is that it cannot localize things well. If you ask it like in a picture, where's the fire hydrant? Which area of the picture? You know, it doesn't really tell you that well because it doesn't have that kind of information inside these embeddings. Okay, the thing that it has is a position embedding. So this position embedding can tell you like, okay, this is piece 0 in the picture, piece 1 in the picture. So that is like, imagine I like cover your eyes and I tell you, okay, this patch is at top left, this one is middle, this one is bottom right. You know, you roughly know what it is. But inside this patch itself, you have no idea where your position is because you don't have the information for that. You only have information at a patch level. So in a broad sense, it's able to tell you the rough characteristics of your picture, but it's not able to go into the details of where specific things are in your picture. And this is the problem that makes the vision language models suffer from a lack of clarity of that picture. And you trace it down, the issue is actually the vision transformer. Okay, we have actually made the embeddings of the patches in such a crude way, and it's only one abstraction space, right? You lose out all this spatial information. Okay? You only have spatial information for these patches, which may not be enough for most cases. Okay, all clear so far? Do you all need me to cover anything else in this vision transformer? Because the paper is actually tackling one of the issues of this vision transformer.
No, that's good.
So, you know, yeah, go ahead.
No, that's fine. That's good. Thank you.
I got one question. So this picture is pretty complicated. Would it work better for like in a cup in a still light, but you capture like several pictures of the cup from several angles, like a 3D, like a flattened 3D image? Would it work better?
So multiple views, right? Instead of one view. I like the idea. And actually, that's also one of the questions to discuss, like how to improve the abstraction spaces that these image models take. So I believe it will improve the result. Okay, just like humans, like when we see an object, like for example, this fan here, I not only see it like that, I actually see at different rotations before sometime in my life, all this form in my memory. So with this amount of views, and then I see it from far and near and so on, this actually helps to improve the how I can make my decision. And of course, there are other things that can affect how you make your decision, like for example, your context. Like now I'm in a room. Okay, if I see a circle object, I might think it's a fan. But if I'm at the beach, if I see a circular object, I might think it's a frisbee. Okay, so it's based on context. Your brain can prime differently to interpret the image differently. Okay, here we don't have the context. Here it's just the image like that. Yeah. So I believe how our brain works is a way whereby different input modalities will influence one another to form some context, and then through some iterative process, you refine onto a solution. So just this vision alone, this is not enough. So this just like you take in the input, but you don't have the context. So maybe a secondary way of doing it is you need to append some context over here and then you have your image or your image and your context so that you can refine how it interprets the image. So yeah, these are some ideas that I have. Yeah. So is that similar to yours?
Yeah. I was also thinking about how your memory soup can help, right? Because we know that when we see certain things, our brain automatically and subconsciously fill in missing information, and we actually see things that we don't see, right? So I don't know if like, with the kind of memory that you were thinking about, you can actually fill in the context, like the most likely context, right? To make sense of an object. That might be helpful, right?
Yeah. So anyway, let's go back to this. So I just want to highlight that a vision transformer way of making the patches is not the best way of doing it. It would be better if there's multi-resolution, different views of the image and so on. But this is what we have right now. This is the state of the art. In my previous sessions, I've been basically criticizing this method. I don't like it at all. It takes away too much information. Okay. So how can we improve on this? So let's forget about all the possible ways to embed. All right. Let's just assume that we are stuck with this for now. We are stuck with this vision transformer way of embedding, okay? Because this is the best method so far. How can we improve using this crude method of embedding? How can we improve vision question answer, which is basically given an image, given a question, answer that question. All right. So that's the purpose of today. All right. How can we improve vision question answer given this embedding? Okay, so just some background, all right? So we have this thing called the large language and vision assistant, LlaVA, and I also intend to cover this in a future session as well because this is quite popular recently. LlaVA, what it does is basically it takes in an image, embeds it into image tokens, okay, using a certain projection. It takes a natural language instruction, which is like text, okay, and it embeds into text tokens. So if you look at it here, these are image tokens. And these are text tokens. So theoretically, they should fall in the same space, okay? Because when you do this image, you actually do like clip embeddings and so on. Actually, when you do the text, you also might use clip embeddings, but clip embeddings for text. This one on the right is clip embeddings for image. So usually people do like they map this into a common space. So this image and text tokens, you can treat it as interchangeable, usually for this multimodal language models. Okay. So what this does is that we have a language model that takes in this as the input tokens. It's something like, like I'm a student, right? Like I am a student, right? This is for text only. So the answer will be like student. But for multimodal large language models, you have like image, then I am a, then the answer will be like maybe student or so. Yeah. So you can output either text tokens or image tokens. And then like if it's text tokens, you could just output text immediately. If it's image tokens, you need some form of decoder to decode back into the image itself. So this image tokens back to image is hard. All right, that's why we have stuff like stable diffusion to try to generate back to the image space. So this in general image space is hard to return to, because once you go to the token space, can you see the vision transformer embedding just now? Once you go into the vision transformer embedding, you lose out so much information. How can you go back to the image space again? It's almost impossible. So you need to use other methods to generate back your image space. Okay, but for text space, it's okay because the text input and the output is the same space. All right. So that's why text is the dominant way of large language models. Right. We haven't quite figured out images yet. So this multimodal large language models, the image part is the one that is a pitfall, because image is a much harder way to process it, because there's just so much information in images. Like you think of it, red, green, blue pixels, position, and so on. So all these are a bit difficult to return back to for images. But in order to do like processing of image and text, you can embed them into this token, the compressed space here. And then output here, as long as your language output here is in text. So the output for multimodal models are usually in text, okay, because it's very hard to return back to the image space. So this is the reason why, all right, when we do vision question answer, we give the image, we give the text, and we get our output back in text also. You normally don't see people get the output back in images. Okay, it's just too hard to return back to the image space from the embeddings. All right, all clear so far for this? Yeah, okay, so this is the background for the whole paper, because the paper is using this LlaVA model, and they use it over this language model called Vicuna 7V, right, which is actually a model that is trained using ChatGPT's outputs, and they just do some instruction fine-tuning based on that. So this is what they use. It's actually not a very good model for, if you try out LlaVA using Vicuna 7V, the capabilities are not that great. So in order for this Vicuna 7V LlaVA model to outperform GPT-4V, there's something interesting in the mechanism they use. All right, and I quite like the mechanism they use. So without further ado, so let's move on to the main paper itself. So how do the authors get such a inferior model to work better than GPT-4V in this kind of situations? Like how? What is the mechanism that is used? So as a brief run through, this is the question that we ask. Like this is the text question for visual QA, and then we also give it the image for the visual QA. And then what will happen is that a first pass, okay, this is the first pass. Okay, the VQA model is trained, okay, to output whether it has sufficient information to answer the question. All right, so if it has sufficient information, the answer will appear, like the color is green or something. But if it's not sufficient, the visual question answer model has been trained to output this format. Sorry, the current visual information is not enough. I need to find something first. So you need to find like a list of objects. So this list of objects basically has been fine-tuned on the Vicuna model, and then they train it over like 100,000 of examples in order to output like relevant list of stuff to find. So in this case, what color of liquid is in the glass? The list of objects is glass that you need to find. Okay, so actually what they did here, they did fine-tuning on Vicuna 7B. Okay, but I think this is inefficient. What we can do is we can just ask GPT to list relevant objects. Because you see, when you look at this okay, this is not in the paper by the way, but this is my view, all right? Look at this. The object that you want to find out is actually the question itself. You don't have to use the image to list the object. You can just straight away from the question itself, basically map the question into an abstraction space that has all the important objects, and then you find each object individually. Okay, because as what I said earlier, vision transformers, the embedding, right, is very, very poor at localization. So if we can add in some form of way to say that, hey, this list of relevant objects are at what location, okay? And you just put it inside here. You look at this, these are the location, right? And we put it inside this query here. It will work much better. So actually the key insight for this whole paper, okay, is that find key objects. Add that as supplementary information for VQA context. And that will, like, maybe that can actually help address some pitfalls of VIT embeddings. So this is, actually, I don't have to go through the rest of the paper. This is the key thing of this paper, all right? The VIT embeddings are not great, but we can supplement it with more information. So this entire paper is about how you can supplement this information. They went through a very, very convoluted step here, which I don't think is completely necessary. But if you are interested to know, these are the steps that are needed. So I will be going through the details later. But the steps that are needed is basically quite human-like, I would say. Like, what they will find out first is that, okay, I need to find out the glass. So where would the glass be? So then you start to recall, the glass is usually on a dining table, okay? Because, I mean, you have the image here. So this part here, you need the image, okay? Because you need to know, like, what are the context of the image. So the glass is likely in the dining table. So I will focus my attention. It's just like when you're trying to find your lost key or something. The key is likely on my table. Then you try to focus your attention. Where's the table? Where's the table? Where's the table? So you see, instead of looking for the glass directly, you look for where the context of the glass should be. Right? The glass is on the dining table. So then we do a divide and conquer. Okay. Here's like, okay, it's actually on this part of the table. Like the table is, let's see where they use. I think they took this part of the image. It's this part of the image. And then when we go here, like, where's the dining table? Where's the dining table? Okay, it looks like it's on this part of the image, like this. And then you move here like that. And then finally, when we reach this part of the image, like, then my localization model, because the image is zoomed in enough, my localization model can finally find out where the glass is. Okay, and then I can crop out this glass and put inside this visual working memory. And I supplement this visual working memory, and then I ask back the vision question answer here. So instead of giving it the question and the main image itself, I also give it the specific target objects that I think can help with the query, and give it the locations as well. So it can answer more questions regarding spatial locations and so on. So this part here, all right, this part here, getting the target objects, getting the target location, okay, and iteratively narrowing down the context by divide and conquer. I think these are the two main things of this paper. So narrowing down of context by divide and conquer, and two, supplementing the information with key objects and locations. These are the two main takeaways from this paper. And I think that this is wonderful. Like the way that they did this is very, very interesting. Okay, I'll pause here for any questions. So I basically described whatever I wanted to talk about today in this one slide. But before we go into the specific details of their mechanism, any general questions you have so far about their mechanism? Or if it's good, you can also say it's clear for you.
All good.
All good. All right, that's good to hear. Thanks. All right, so let's move on. Okay, I hope you are interested to read this paper because it was quite interesting for me to read it. All right, so how do we first check, okay, whether we need to engage? Okay, there are two models here that we need to engage. Okay, one model is the visual QA model, visual question answer model, that answers this question directly. The second model here is the visual search model, which searches for the objects itself. So the thing is, this visual question answer will always be done. Okay, this one will always be done. But this mechanism here, this visual search to find target objects, only activated when necessary. Okay. So actually in this sense, in the paper, they try to link this to system 1, system 2 also. So it's like, the mechanism that doesn't need the search is system 1, and the mechanism that needs the search and refining the context, that's system 2. And yeah, I think that's I guess this engages some deliberate thinking. So yeah, that looks like system 2 to me.
It
Yeah,
seems like a really good way to work. Like I really like that idea. How do they distinguish when it's time to get the contextual sort of guide going? What's the decision that goes, you know what, VQA is not going to cut it. I need some assistance or a few hints. How do they make that distinction?
Oh, actually, they just use the vicuna itself, but they fine-tune on like 100,000 examples to output these specific words if there's not enough context, and then they train it to output some list of objects here. So I would say this is actually the downfall of this paper, because this vicuna 7B model is not that great.
Yeah,
So
it's not that.
yeah, I was thinking, if you ask, if you can ask GPT-4V, or just chat GPT itself, what are important objects to focus on based on the question, then you can already do this first step, without doing this fine-tuning process that they did. You can just use the GPT-4V model. If you want the image context inside, you can ask what are the important objects based on this question. Then it's like some form of changing of the input space. Okay, from this glass, from this thing here to you have another abstraction space here. So this is the abstraction space. And this abstraction space inside here, you can contain like important objects are glass. So instead of the global question, we focus on the abstraction space. And in order to get this abstraction space, many methods to do. One is an image model like GPT-4V. That's the most best context. The others is just purely based on the text. You can really get this abstraction space. Yeah.
Just
so
guessing. There's probably, if there's a glass, there's probably a table. If there's not a table, there's a shelf. If there's something like that.
Yeah, you could potentially do guessing. Yeah. So if you try GPT-4 V, sometimes it gives the answer just purely based on the text alone. Because I asked it before, like I went to the beach, I took a photo of a hole on the beach, and I asked it like, what is this hole at the beach about? Then it gave me an answer about crabs and mudscapers, not mudscapers, a list of sea animals that might dig holes. And I asked the same question again without the picture, and it gave me the same list. So I have a feeling that just based on the text alone, sometimes it might be sufficient already to determine the context. Yeah. So I think this method that they propose is interesting and good, but we don't have to use the way they did it, because the way they did it is too convoluted. So we can just ask like a zero-shot question to get into this abstraction space, and then we can ask GPT-4V multiple questions on this abstraction space. So in some sense, we are giving it more views by asking it more, like this is okay, this part here at the beginning, this is the broad context. And then when we ask into the abstraction space here, this one will become the specific context. So we have a broad to specific asking, and eventually all of this together, okay, will combine. Yeah, so as I was saying before the thing cut off, I think this idea of increasing the context by asking it relevant questions. So for example, we can form an abstraction space of important objects, like for example, the glass. So this is a very interesting idea, and this is definitely something that can be done even with GPT-4V, right? We can ask guiding questions using GPT-4V or ChatGPT if you just want text only. All right, you can ask the guiding questions and ask it to give responses about like what are the important objects. Then you can do visual QA over these important objects, okay, in order to find out more information. Or like if you want to extract out the bounding boxes and so on, you can do that here. Then in the end, what you do, you combine both of them together to form a supplementary information, supplemented context, okay, for better question answer. So I like this idea a lot of augmenting the context by just increasing the amount of information that are relevant to this question. So this is something that is quite exciting about their whole method. Okay, granted, we don't have to use the same way that they did it here, like to use the fine-tuning to get the answer like that, or to use like a lot of like divide and conquer methods to find out the specific part of the image. Okay, if let's say the the vision models improve, this LLM guided search here may not be needed anymore, right? But let's say we still are stuck with vision transformer embeddings, then this method of divide and conquer will help to eliminate some of the issues of localization for vision transformers, because the more you zoom in, the better context information of the location you have, because when you group by patches at a more zoom in image, you get the location better. You get top left, top right, bottom left, bottom right when you zoom in more. So this one, this part here may not be needed in the future with better performing vision models. Okay, but this idea of supplementing your context, your question with relevant information, and then using all this supplemented context to answer the question, like for what they did here in the vision working memory, they have the main question, the global image, the localized images of the target objects, and the locations of the target objects. I think this method is good. Okay, so this is the key takeaways that we can have for this paper. Any questions here before we move on?
Looks good.
All right, so I'm excited to cover through the main thing. So the main procedure is we first ask our vision question answer model, okay, whether or not the visual features would suffice for answering the question. So this is, as I said, trained using fine tuning. Okay, if yes, the answer is yes, then we answer the question directly. If not, we list out all the needed but missing information in the format of a list of target objects. So this is the first part that I was describing. So how do we do this visual search? Okay, we do a visual search by finding out these search targets one by one. So there are 4 blocks of the memory that is stored for the visual search so that it can be used to ask the visual question answer model to answer the question. The first block is the question block, which is the main question itself. The second block is the global image block, which gives the original image. The third block is the search target block, which basically crops the target objects to basically give it a better resolution of the image. And then lastly, we have the location, because as I said earlier, vision transformers are not very good with specific locations because of the way we do the embeddings. So this is done using a visual search model, which actually in the paper is also the same model as the visual QA model. It's also a LlaVA model. Okay, and that is based on Vicuna 7B. So what they do is they use this model to identify the objects. Okay, and this actually can be replaced with any multimodal large language model. As long as you can take in text tokens and image tokens and output some text tokens, you can use this model to do your visual search. Okay, okay, not just text tokens here, because if you look at the next few slides, there will be one slide that shows like heat maps and everything. So they actually do something more complicated than just text token output. So this is the visual search procedure, and this is the slide that I'm talking about. Okay, this is the slide in the entire paper that they did not describe much about, but this is actually one of their most important slides. I'm sorry, this is also one of their most important model architecture. So there are 2 things that they do for the visual search model. So before I go into the details, I'll just tell you roughly what it does, all right? So this identifies bounding boxes for target objects. So I mean, this is something very similar to YOLO. You only look once, you take in the image itself. In this case, because of vision transformer embeddings, it takes in image patches in the form of image tokens. Okay, but essentially you are trying to identify the top left, bottom right coordinates of images, or bottom left, top right. Okay, I can't remember which is which, but the idea is you are identifying the bounding boxes for your image. So let's say this is your image here. Your image is here. So what you do is basically you give it the Q that you want. Like for example, I want to find maybe I would like to find the 8. Okay, or like a context specific, like maybe it's a monkey with 2 hands or something, or like sitting on a chair near a chair. I mean, if let's say we have a context, we put in this context here in this VTL and this VCL. It's actually the same location information but mapped using different basically the different MLP is basically mapped into this, because different models might have it in a different abstraction space, so they map it differently. But the idea is like, given this, you want to find an 8, right? So what it will do for this localization model is that they will localize some images, localize some bounding boxes, and for each of this bounding box, you take the patch and then you see how similar it is to this description here, and then you can map how similar the patch is. So like for example, if this is this an 8, 0.3, okay, it's similar only by 0.3 by the image tokens. This one 8, 0.9. So what this means is that, you know, when I want to find out which image to crop, okay, so this actually helps you to find out which part of the image to crop. So essentially this is fulfilling the part of cropping out the target objects part for the visual search model that you saw in the earlier slide. They have this list of target, this one, search targets and target location. This is the part of the model that crops out the image for you. Okay, the exact details quite complicated. Okay, I believe it's done using the YOLO method. Okay, although it's not stated anywhere in the paper. Okay, I try to dig in the code also. It's not very obvious where this is, but I can just treat this as a black box for now because this is not the main part of the paper. You just need to know that given an image, we are just trying to extract out bounding boxes that contain the target objects. So that is the target localization decoder, right? And then for each patch, we also score it according to how similar this patch tokens is, okay, compared to like the original context that we want to find out. So that's the target localization decoder. Okay, I might have gotten some details wrong here because the paper honestly didn't talk anything much about this. Okay, but I believe the rough idea I'm describing is correct, right? So next, the search queue localization decoder. They did mention that it's similar to the segment anything model by Meta, and that's about it. No description of how this is done. But you look at the architecture here, you can see roughly how this is done. Basically, you take in the image tokens. Okay, you take in the context tokens. You do some form of cross attention across the image tokens and the context tokens to find out which is the most important parts. All right. So the image tokens, these are basically something like your document retrieval. Okay. And then like this could be a database. And then like down here, this is your query in order to find out which document to extract. So using cross attention, you know, you try to find out which is the more important ones. And then here upsample is just to make the make it into the same dimension as maybe your bottom. Yeah. So the thing is eventually in the end, what we'll get is a heat map. So we'll get a heat map for each pixel in the image, how similar it is to the query. That's all we need to know. So this is basically a way to, you know, the segment anything model by Meta, they output a mask. And the mask is basically like, this is a mask for a dog, this is a mask for a plate, and so on. So this exact process is just to generate a mask for each pixel. Okay, how similar it is to maybe the 8. So you can get a heat map of where the 8 is. Okay, and what is this heat map used for? Okay, the heat map is not used for getting your bounding boxes. Okay, that is the target localization decoder. What is this heat map used for? The heat map is used to select which sub-image to focus on for the subsequent visual search. Okay, so basically they did a summation of the of this heat map here, and this summation score will be your like priority score. So the higher the heat map score, basically the higher it is, that means the more similar it is to this query or to the context. The higher this score, the more likely you will want to search that part of the image. So I'll describe this later, but the idea is to choose which part of the image to focus our attention to in the subsequent searches. Okay, any questions so far on this slide? This is a very complicated slide. Yeah, I'm very sure I did not cover all the details fully because I don't intend to. Okay, but so far, do you all understand this slide? Is it clear? Good. Okay.
I think so. Look, it like as you say, it's very like the implementation's hard. The idea is pretty, like basically, RAG by another name.
Yeah. I mean, you can think of it. Yeah, this is rack over pixels, and then over on the left here, this is a bounding box localization.
Yeah.
Okay, so eventually, once we get everything done, all right, we search through the visual search model multiple times. Yeah, we'll run through that process later. after we search through multiple times, we can then feed everything back into a transformer. And this transformer is the visual QA model, visual question answer transformer. And in this paper is Vicuna 7B, okay? Using the LlaVA method, which is basically the method that combines image tokens and text tokens together. All right. So there's a lot of things to unpack in this paper, but the key idea is that we feed in extra context into this transformer model. So we feed in this text into here. Okay, we feed in the global image here, which is basically the original image. The sub-images with their locations we feed in here. And then after we feed in all the image and all their locations, then we ask the question, hey, is the orange luggage on the left side of the black luggage? So over here, you already have stuff like, this is your orange image, your orange luggage stuff. And then you have your black luggage stuff here. And then over here at the front is your overall picture. So it is quite nice. I would say the prompting format is quite nice, and something we can learn from is that you have the global context first. Then you zoom into the local context. And finally, you ask everything first before the question. So this is very similar to the style of prompting that I would do for large language models. You go from the broad prompting, broad context, all the way to the specific context, because when we focus on this specific context, we can take in stuff from the earlier parts. You all know about the language model usually, like for GPT-like models, it's called a causal language model, because you can only attend to tokens before it. All right. So in order for the specific context to attend to the global context, you kind of need to put the global context first. Then you go to the specific context. So this style of prompting for the language model, I approve of it, because it's exactly the same kind of format that you would need to do language model prompting for text as well. So we can learn something from this. All right. Okay, so what this really means, okay, is a bit hard to visualize like that, what it means, but what it actually means is that you have some image tokens, okay, and then you have some text tokens like additional visual information to focus on, the name of the object, and then you have the image tokens here. So anything to do with this angle brackets, you replace with the image tokens, okay, that is using the clip embeddings, right? And basically you ask the question. So you can think of it as a normal language model with text. It's just that there's extra image tokens inside, right? So this is exactly what the multimodal language model is doing, right? Easy, right? You just replace the image with image tokens. Okay, the hard part is how to get the image tokens. And right now, I would say that there's no way of getting image tokens that is really good. Okay, our image processing capabilities are not great as of now for this kind of transformer models. But with this limited list limitations that we have, we can still do decent jobs at most things. Okay, so I think this is something that quite cool, because it solves a lot of problems of the embeddings. It has the location information here, which is a super good plus. All right, and it also has the ability to get the target objects like that, which is also a plus, because if you just give it the global object itself, you might not be able to get the details well. So I really like this method of prompting. Okay, this is the question right now we need to ask ourselves, like, what if our visual search cannot find the object? All right, so what we can do is, okay, if we cannot find the target object from the first pass of the image, all right, what we can do is we can ask some guiding questions. So they'll ask the visual search model, what is the most likely location of the target object in the image? So like if my localization model cannot find the object at all, I ask the visual search model, the Vicuna 7B model, what is the most likely location of maybe the ape in the image? And then the visual search model will output, the ape is found near the chair. All right. So like, for example, if I put like, what's the ape, and then the ape is found near the chair. So please locate the chair in the image. Yeah, so for example, this is the thing. So instead of finding the original object itself, we find the contextual cue, which could be easier to find because this might be a bigger object, right? So what we do now is we'll split the image into 4 parts. Okay, we'll assign a priority score based on the confidence of the patches, okay, from visual search model. This is actually based on the heat map. All right, we add in these images to the buffer, and then we keep searching the buffer until target image found, or the image size is too small. Okay, quite complicated stuff to unpack. No worries, I prepared an example to show you. Okay, so let's look at this image that we saw earlier that they said that, this is better than GPT-4V. Okay, they can say that the ape is holding a guitar, right? GPT-4V says the ape is holding a saxophone. So yeah, I tried it out on GPT-4V. What they say is really true. GPT-4V cannot answer this question, but theirs can. Okay, so how did they do this? So they split the image actually. So basically, if your first image, you cannot find the object itself, you cannot localize the ape. What we'll do is then we'll ask some contextual cues to say that, like where's the ape? So maybe you can say the ape is on the chair or something. Yeah. So the thing is, okay, just to let you know, this priority here is entirely made up. Okay, because I don't have the actual priorities in the model output. So I just give some example of how this would be done theoretically. So the main thing here is once you want to find an ape, we will get some form of heat map of the image. And let's say the heat map says that, the ape is somewhere here. So the priority score here will be very high because if you sum up the density of all these heat maps, okay, this will be much higher than all the other regions because the ape is really here, right? Maybe here there's an ape also. So this part here might be high also. But this part here is the highest because this part, the ape is the biggest. So we can assign the priority and, like for humans, if you want to find out where the object is, and you split the image arbitrarily into 4 parts. Like which part do you want to focus your attention on? The one with the highest priority, right? So similarly, in this case, we have this part of the image, the bottom right with the highest priority. We want to focus there. So let's focus there. Let's zoom in onto this image. Okay, now we zoom into the image. And you know what? We still can't find the ape. All right. So what we do now is we do the same thing. We do the heat map again to see where the ape is. And we realize that the ape is here in the heat map. All right. So you know what? Where should we look into next? Here, maybe you should look into here now. So let's zoom into this part here again. And finally, our localization model has localized the ape. Look at that. We have localized it. Okay, we have some coordinates at the bottom left and the top right. Okay, I might have gotten the coordinates wrong. It might be top left, bottom right. Okay, but the idea is similar. You have the coordinates from the localization model, and you can crop out the image. And all this will be supplemented to your visual question answer model to answer the question with these localized images. So so far this is the first demonstration. Any questions so far on this demonstration? So basically when we want to search the target object, we cannot find it. So we ask like guiding questions and then we search for the guiding question in the heat map. And also the localization part, we search for it and we cannot find it, zoom in, cannot find it, zoom in, finally you find it, you get the bounding box. So in this process, is it clear for you? Yeah, can I get some response so that I know that?
I was just going to say, I've done a little bit of work on object detection and stuff, sort of less transformer based, just old school varieties, and it's a very similar algorithm, right? Just try a bounding box. Do you find a thing you recognize? No. Try another bounding box, right? Keep going. And the question comes down to how do you manage the search, and do you have a good way to recognize a thing when it turns up anyway?
Yeah,
right?
correct. So did the old school algorithms also like subdivide the images into parts and search those parts?
Yeah, they do. They're really, so that's in my experience anyway. Like I'm a beginner at that stuff, but yeah, it's just a lot of the research revolves around what's a more efficient or effective way to slice up the image so you can come up with a bounding box. Right? The whole, yeah. Do we go? Yeah, what are you looking for? Might change. So if you're doing OCR, for instance, you might choose like a sort of clockwise spiral golden mean kind of thing till you find a thing that looks like text. Unless you're looking for right to left text, in which case you'd go the other way around the spiral. Right? So just because you expect it's going to follow one of those two patterns. If you don't know what you're looking for, do both. Right? So so it's just a question of which boxes do you try, and can you get. I mean, that's why computer vision for so long was such a challenge, was because if you don't have an adequate way to recognize something, it doesn't really matter how you index the image, you're never going to find it. And so, people use neural networks and whatever they could come up with, or all kinds of image treatments around color and density and whatever you can think of, in order to improve the image such that relevant components of the image can be dragged out of it so that they can be processed. So a whole bunch of things on edge detection and God knows what. And just changing the orientation of something, I mean, would and still does make it very difficult to identify.
Yeah. So I think this whole part about images thing is still largely unsolved because we still haven't found the perfect way to do it. But one thing for sure is that the method that is proposed here to, I think, subdivide the image and focus on the subparts, I think is a useful one because the image models can generally identify stuff when it's like of a bigger size. I mean, it depends on the training set actually. If your training set has very, very small resolution stuff, maybe it can do those also. But in general, like even for humans also the same thing. Like if you can focus more on the stuff that you want to find, it's easier to find it. It's like doing some some filtering based on like what you want to find, and then you filter away all the noise. So I think this method of iterative focusing might be a good one. So yeah, let's go to the example that they showed on the paper. So this is the thing that they want to find. So they want to find the guard, okay, but cannot find the guard in this picture because it's so small. All right, is it that even in my own eyes, I can't see the guard from this original context. So based on the picture, the guard is most likely to appear next to the building. So that's the Q. And this is the heat map that we see here. So based on this contextual Q, find out where the building is, because you can see this is the heat map generated by the segment anything model, the same architecture. So this basically generates where the building is. Like you can see, it's quite nice, right? They identified most of the building correctly. So the guard might be here. So if you divide the image into 4 parts, right? Where is the most likely part where the mist is? Okay, it's either here. It's either number 1 or number 2, right? Because this is where we should focus our attention on. This is where the building appears. So knowing that, let's zoom inside the part of the building that represents it. So what they've decided to do, okay, take a look at this. What they have decided to do is to focus on this part here. Because this is where, the smoke is the densest, or the mass is the densest. So if you sum up the heat map values, you realize this is the highest. So we focus on this part. So now that we focus on the top left quadrant, okay, we ask again, what's the guiding questions, okay? The guard is most likely to appear near the entrance of the building. So now, before that, you can see appear next to the building, right? Now we zoom in here, we can see that there's an entrance somewhere here. So the guard is most likely to appear near the entrance. We have updated our contextual Q, which is kind of cool, right? Because like once you zoom in, you can see more things. You can update your belief of where the object is, the guard is. So again, we use the heat map generated. Okay, we still cannot localize the guard based on this contextual Q. We still cannot localize. So still unable to localize. But actually, so what we'll do is we use the heat map and then we try to divide the image again into 4 parts. Where do you think I should focus on? Anyone can tell me? 1, 2, 3, or 4. Which quadrant should I focus on to find the guard?
Yeah, let's go with 4.
Yeah, most probably is 4, right? Because the 4 has the densest heat and entrance of the building. You can see that based on this entrance of the building, you have updated your heat map to be like here. So this part here is no longer there anymore. So it's quite cool. Like based on stuff like entrance, you can update your heat map accordingly. I think this is It's very, very interesting. Yeah. So now we have zoomed into the fourth quadrant here of the image. And now I search for the guard. And guess what? Guard is spotted. I have my bounding box. My localization model has found the guard. Right? And because the localization model has found it, I have no need to do the heat map anymore. So if let's say cannot find it, I'll do the heat map and do it in the 4 quadrants. Okay, but there is a limit to how small your image should be. Yeah, because if you zoom in all the way, you see stuff that is like, imagine you zoom in all the way, you continue, allow your algorithm continue until you zoom into something like here, this window here. You know, it's not exactly going to be very useful. And besides, the search depth will be increased so much, your algorithm will take very long to run. Okay, right now, I run this algorithm, it takes about 20 to 30 seconds on average. On some edge cases, it can take up to 90 to 100 seconds. So that's quite slow, actually. So you don't want the algorithm to run all the way to the end, like when it sees nothing. You maybe want to cap it at, like maybe this could be your final image resolution that you want to cap it at. So these are some practical concerns regarding the iterative search algorithm. But the idea is very similar for the visual search.
I was going to say in real time at the moment, I don't know if you call it, on the market, you can expect to get a camera which has real-time bounding boxes of people.
Yeah, that's YOLO. Yeah, YOLO V8 can do that.
Yeah, so the number one manufacturer come out of China, they do a really good job of it, and they can draw those bounding boxes in real time, which makes this. So if you took that as a given, right? So the conversation becomes a little different. If you've got, it's just of the people in this video, because they work real time, which one is most likely to be the guard?
Yeah, that's very cool. Actually, that's also one of the discussion questions I have. What if we have video? Can we do something even more cooler with video? Yeah, because with video, you can compare 2 successive frames, right? You can perhaps identify objects more easily by their movement.
Yeah, there's a whole thing on gait analysis and so on. So you might say that, you know, in front of Buckingham Palace, you might find the guards tend to march instead of walk, right? Or you might have to distinguish between police and Marines because they wear different uniforms. So you have and they stand in different places and different things happen, right? So, but in terms of monitoring of people's behavior, there's a whole field which is now out in the wild commercially. And so it's not there's more to dig into this. I think what's interesting is the way, in particular around this, is the conversation around how it overlaps into large language models and transformer-based sort of latent spaces. Because I don't know the techniques they use today for the computer vision stuff, but they're very effective, right? And so they're not very good at saying that's a guard and that's not. The people put a lot of work into making them find people and number plates and other stuff in real time on video. So then there's these over time analyses that come up. Where gait analysis is one where people have, you know, the tinfoil hat brigade will walk around with a pebble in their shoe to make them walk funny, right? So, so it's hard. They present a different profile on a gait analysis, right? And then but it's sort of that's one of the biometric features that turns up in video over time.
Okay, yeah, cool. I think that's a great thing to look into, like how to do this kind of real-time analysis using this method. Yeah, that'll be a very big improvement to the way we can do this visual question answer. So in the form of videos. So let's move on. So just want to highlight that the way that they are doing the search right now, it's a form of best first search. So based on every time we go to an image, we'll add in like the 4 sub images into the buffer. So like for this image, if we cannot find the object, we'll add in this sub image 1, sub image 2, sub image 3, sub image 4 into the buffer. And the thing is based on the heat map, okay, I can find which quadrant of the image I should look into first. And then again, I can split into 4 quadrants. Let's call it quadrant A. I use a different color. Quadrant A, quadrant B, quadrant C, and quadrant D. So you can then group into another 4 quadrants, and then you can focus on the image that is of the highest priority based on the heat map, if you cannot find your localization. And then eventually, once you reach small enough, hopefully your localization model can find the image. So this is the idea. If we look at it practically, you actually only need to run it 2 times. Because if we go by the highest priority in the buffer, you only search the 0.9 and 0.9, you find your image. The only problem is that after you search, and then you cannot find at the lowest resolution of the tree, you need to search another branch of the image and keep finding and finding. You know, if you search through, let's say if you have a depth of 2 like that, you actually need to search through a total of 16 sub-images. So if let's say your best first search doesn't find the answer straight away, you know, it might take very long. So that explains some runtime of 90, 100 seconds. I think they did up to depth 3. So, you know, if you can, if your depth is too high, okay, and you cannot find your image using best first search straight away, you need to keep going through other branches. You can end up with a very, very long runtime, right? But the idea of focusing your efforts on where it deems best based on a heat map, which is basically a mask decoder to see where the contextual queue is likely at. I think that idea is a very powerful one because it forms some form of heuristics. Okay, the heat map forms the heuristics to guide your image search. And that's why they call their algorithm V star, because in A star algorithm, which node you choose is a combination of your current score plus a heuristic, okay, to angle, like a distance to the angle. So in A star, they do this. Okay, here you don't really have a combination of your current score because you don't have any like cost function up to now. So they don't really have this part here. We don't have this in V star. So V star, what they actually have, they only have the heuristic to the end goal, like how far it is to the end goal. So how similar, so the heuristic is basically how similar image patches to the contextual queue. So that is the heuristic they use using the heat map. And I think that is a very, very good idea. Yeah, I quite like this idea of focusing. But here's what I like to tickle your minds. What if the object breaks in between the 2 quadrants? All right, so think about it. If let's say I want to find a teddy bear, right? Like let's say I want to find this teddy bear here. And this teddy bear is in between 2 quadrants. How? Right, but I do this method, right? End up I will localize only either the top half or the bottom half of the teddy bear, right? So this method is not without its flaws. It's
the classic solution in computer vision is do more swatches. You do like twice as many. So you have 4, 1 for each quadrant. Then you also have cardinal swatches, so north, east, south, west. And
yeah,
and the classic solution is do more, right? And one of them, one version goes, you take a fixed size bounding box, and you just move it 1 pixel at a time. And if that doesn't find what you're looking for, choose another size bounding box and move it 1 pixel at a time. And like it's really like they're not, the base techniques are pretty basic. they're not too clever. And they do an awful lot of repetition and finding nothing.
Yeah. So I mean, we can also solve it using something like that. We can shift the grids instead of the image segmenting like that. We can segment like this. You know, we could segment in different ways, cardinality and so on. We can change the bounding box size. Instead of doing quadrants, maybe we can do by rectangles and so on. I mean, there are different ways to bypass this, but the main point I want to highlight is that even such a way of focusing using quadrants comes with its limitations. And the key reason why this kind of works for most of the images they use, okay, is because the data set they train on uses objects to localize that are very, very small. So the chance of it being cut by this line is very low. So actually this the evaluation data set for this V-star is kind of biased because
I
they
think
only
I have an idea. I was wondering about the same problem, and I think one of the ways they could potentially address it is by taking the heat map and then making the bounding box of the heat map, and that's the new crop. And then you could put a constraint on the localization statement that the contextual cue, as you call it, sorry, is where it must be more specific than the previous one.
Oh, that's a very interesting idea. Yeah, I think the authors would benefit from this because I think this is quite easily done. And
Yeah, that's what I mean. That like, if they, I mean, what's interesting here is the way they pulled together these two ideas and they've done it. It works. Well done. Like, but now we get into the optimization questions of how do you want to do it?
I like your method a lot more. Actually, with your method, we don't even need to do the best first search. We just basically based on the heat map, go to the next part, then go to the next part and go to the next part. We can just do a one-step process. Because if let's say any step fail in the pipeline means I don't think you'll find your target object anyway. So
or perhaps the heat map was in the wrong place, right? So if the contextual clue said, for instance, you'll probably find a guard on the pavement, it'll never find them.
yeah. So maybe instead of doing a best first search like this, okay, we don't do like that. What we'll do is we give like maybe 2 to 3 contextual cues, and then we just run down one path.
At a time, yeah.
Yeah, so like maybe for the guard one, the guard could be like on the pavement. That's clue 1. That's Q1. Near the building, Q2. And maybe like at the door, Q3. So basically we ask the language model to come up with 3 different queues, and then we just go through the queues one by one. And then at each level, we split again into 3 more queues, and at each level, we're more and more specific than the first level. I like the idea a lot. Yeah, I like the idea a lot.
So, yeah, anyway, I mean, but yeah, they've built theirs and it works, so I'm not going to argue too much. But in terms of ways we can optimize, there's sort of, they prove the point. So the question is now, what do you want to do about it, right?
Yeah, I like this a lot. Actually, this we don't even need to use their method to implement this. We can implement it on GPT-4V already. Like we can basically ask GPT-4V to say that like, okay, we basically can split the image into 4 parts for GPT-4V and say like, which subpart contains the guard, or like which is the highest probability. Yeah, I mean because we can't modify the internal model, but I'm quite sure you can prompt it such that it can identify how to split correctly. Or what we can do is we can pass it through the segment anything model heat map. All right, then based on the heat map, and then you localize that bounding box based on the heat map, you can pass that crop image into GPT-4V.
Yep.
So we can do this process ourselves with just the segment anything model, the mask decoder to get the mask. And GPT-4V, we can actually improve on the performance of this paper like significantly already.
Maybe.
Yeah. So I mean, I just want to finish typing.
Go on. Yeah.
Yeah. So just to make the queues more specific. Maybe this could be like Q1, Q2. Like so, for example, okay, we are talking about near the building. All right. So near the building is near the entrance of building. Okay, near the exit of building. Yeah. So the queues could be more and more specific near the like what near the window of building. Yeah. So with this specific queues, we can actually guide the search to be more and more specific. Yeah, I like this idea a lot. It's actually better than the method they propose in the paper, because the method in the paper is by quadrants, which can cut off that image. This method, with using the heat map as bounding box, I think this method will work better because it doesn't cut off the image.
The question is, it has to be, so it doesn't have to be more specific than the last queue. It has to refer to some sub part of this image. So as you crop, like for instance, in this one they did quadrants, whatever. we drop off the pavement and it's just about the building and behind the fence. So you can't talk about not on the pavement anymore. The context is different, so you need a new cue. So it's not necessarily more specific, but it has to describe the most relevant available objects, things, references in the picture that would relate to the guard, for instance. Right, so the objective is find the next best crop.
Yes, correct.
So
And we can set it such that the heat map, you must crop like at least 50% of the image. Yeah, so
something like that.
we can make it a hard limit so that we can drastically reduce the search space each iteration.
Yep.
Yeah, great. So we just enhance their model. Although we have no experiments to prove it, but yeah, that was a great discussion. I agree with this method that we discussed more than the original paper. Okay, so let's sum up the entire paper. All right, the paper basically, you have basically a model, all right, and this model, you supplement it with your search targets and target location. We ask the language model. Okay, this resampler and linear, you don't have to worry too much about it. This resampler is basically compression. It compresses the original image so that it doesn't use up so many tokens. Okay, but this is not the key point of the model. The key point is that what we do is we take in the original image, original question, we supplement it with other objects, like the target objects, to supplement the context. So this is a key idea of this paper. And how do we get these target objects? We use iterative search. We ask the visual search model, which is in this case, Vicuna 7B in using the LlaVA method. Okay, we ask it to suggest the contextual cues of the image if it's not able to localize the luggage. Okay, then next to the person, right? So after that, locate this person. And then after that, what we'll do is we will ask like it to generate a heat map again to, to find out which quadrant to eliminate. And then after we generate a heat map, we realize, okay, the heat map, maybe it's better to use this quadrant. So it's like that. And then eventually when we can localize, we will localize the object straight away here. So this iterative search process that uses the heat map to crop the image into subsections and then eventually localize the object. I think this is something quite powerful. And, just now Richard and I, we just discussed another method that might be better, which is using the heat map itself to do the cropping of the image and also getting the contextual cues, all right, rather than doing by quadrants. Okay, we can do the best first search by suggesting the contextual cues and then going through different pathways of each contextual cue so as to like do some form of different abstraction spaces. So cool ideas. I do think this visual search can be improved, but the idea of visual search of narrowing down the search space is a good idea. All right, and supplementing more context into the language model, okay, which is here, supplementing specific context into the QA is a good idea. So these are the two main takeaways. Okay, I just reiterate the same as what we talked about at the beginning. These are the two key takeaways of this paper. Exact mechanisms of how they implement, we don't have to copy because I think it's too complicated how they implemented it. But the broad framework, I think they got it right. All right, so let's compare with how this is done in other methods. So for example, chain of thought. Chain of thought typically is like the let's think step by step. But the original paper for chain of thought is like they give some few short examples of how to do like math problems, like start with 5 balls, 2 cans of 3 tennis balls, and so on. So the chain of thought idea is basically like you ask it to think in a more detailed abstraction space. And this idea of going down into more detailed stuff helps it to improve the performance. So you can see that you can solve more complex math problems, all right? Because it can think step by step. So I mean, the more popular phrase for this chain of thought is let's think step by step. Okay, I don't quite like this approach because it's too vague. Okay, this few short prompting is actually better. But even so, this chain of thought, it only goes through one cycle of reasoning because like once it steps down into the abstraction spaces, it doesn't go back up. You see, it just from top level broad go to specific. It doesn't like search other branches of the abstraction space. So this V-star algorithm, they manage to search different quadrants of the image, and then they can backtrack if you don't find it. So in some sense, it can do the backtracking and do another branch. I think it's superior to chain of thought, right? I mean, it'll eventually, when we implement the method that Richard and I were discussing about, it will be superior to their V-star model. But this idea of V-star being able to backtrack and finding the best first search, this one, it makes it better than chain of thought already. Next, React framework. So in the React framework, is the React reasoning and acting framework. Basically, it has been found out that large language models don't really do the environment observations well. So you need to feed in the observations from your environment back to the model itself. Like, for example, here, if you switch on the remote, you know, what is the remote doing? Yeah, or when you search the front row, can you find it? So if you give it the representations of the environment, this can ground the large language model in interpreting it. Okay, so this thought here is something like chain of thought. So it is like thinks about how to get the action. Then it outputs the action here. So this method of thought, action, observation, thought, action, observation is something like the chain of thought, but you chain of thought many times because this is one chain of thought. All right. And then you can do a multiple chain of thought based on the observation reaction. Okay, but there's a difference between this and V-star, is that the observation space of React is not reduced. You realize that the observation here is still the whole environment itself. What V-star does is that it crops a subset of the environment. So this is something that I think could be implemented if we want to do some form of attention-based mechanism to find out what we want to do for this snapshot of time. So the React framework could potentially be improved by cropping the observation to focus on what is needed. So I think there's some ideas that we can take from this V-star paper to even improve on React. So just a quick word on the results. I don't want to harp on it too much, okay, because all research papers would say that their results are the greatest and the best. You can see that, you know, they say that, oh, I beat GPT-4V and so on. They even beat using this LLM tool using pipelines, which is something noteworthy. Is basically text representations of the image. Okay, so even the text representations fail, and later I'll explain why. It's because the images that they use are purposely chosen such that the objects are very, very small. So if you use image captioning stuff, it will fail to caption those very small images. So their benchmark was designed to make their model the best out of all the multimodal language models. Yeah,
I'm shocked.
Why are you shocked?
Oh, I'm not. That was my sarcastic, I'm shocked voice. Like,
Yeah.
it's like someone fiddled a benchmark. Quick, do they come from Volkswagen? I don't know. No.
Yeah, I mean, it's impressive. I mean, even though their benchmark is like biased to suit them, it's still impressive that they managed to beat GPT-4V in certain areas. But that is actually a problem with the vision transformer embeddings. So their paper is tackling that issue. So I still think there's some merit in their paper, although their benchmark might be a bit biased. All right. So yeah, it even beats like open source large language models without their visual search mechanism. So if you don't give the target objects and so on, it's such a huge gain actually. You see, like the latest better performing model, the LlaVA, you see there's even 30% gain. All right. And that's a huge amount. So using this visual search algorithm to get more specific objects, I think that's quite helpful. All right. And yeah, even GPT-4V, it beats. But you can see GPT-4V, even though the benchmark was biased against them, you know, they still did quite well. So, so I think GPT-4V is still much better. So why do I say their benchmark is biased? All right. Because they basically have this attribute recognition and spatial relationship stars. And the attribute recognition is to find an object. But if you look at examples they give, the object is so tiny. All right, it's purposely meant to make the the image processing model hard to find the object. Okay, because the object is bigger, GPT-4V can solve it. All right, and spatial relationship is something that is poor in GPT-4V as well. Primarily because if GPT-4V uses vision transformer embeddings, apart from the patch embeddings position, it will not have any information about where the objects are in the image. Okay, so this localizing small parts of the image favors their model because their visual search model will crop the image, so it becomes bigger in their search space. and they use multiple choice answers. So multiple choice answers will make an inferior model have a chance of competing against a stronger model, because you give it multiple choice A, B, C, D, the chance of it getting right by matching the semantics space of the options to the image will be higher than just a free-form answer itself. So these are some of the things that make me doubt the results of the paper, to basically say that, like, is it really that great? Yeah, the answer is probably not, right? It's probably biased to suit their paper. So this is actually a problem with academic publishing. Academic papers typically want to say that they are the best, they are the most novel, but sometimes you don't really need to do that. Sometimes you just need to propose a very interesting idea like what this paper is doing. But unfortunately, in order for papers to be accepted, sometimes you need to show that you are the best. And performance measures like this, are tweaked for academic publishing. Okay, but if you want a more realistic measure, you cannot just do like that. I mean, multiple choice is not going to cut for most real world cases. Yeah, it's a bit too restrictive.
If you, it's not limited to academia. I name checked Volkswagen earlier for their issues with fiddling emissions tests for diesel engines. So they had I think for those guys, it was a special program that was trained to recognize when they were doing the standardized benchmark for an emissions test and run the engine impossibly lean. So it'd keep ticking over, but it didn't use any fuel. And if you drove in any other conditions, then it used completely different parameters.
Yeah.
So they ended up in court. Huge lawsuit, was ugly. Went on for a decade or something. Like it's not an academic problem. It's a marketing problem.
But I would say that it's pretty impressive how they already beat in these areas. I mean, even finding an aspect to beat GPT-4V, I think it's hard. So I would give some credit to this paper, although I wouldn't say that their model is better than GPT-4V. It's just maybe in this particular aspect, it could be better. But even so, subsequent experiments that I'm going to show you, okay, which I've done, show that we can actually incorporate this into GPT-4V easily. So this is my hypothesis. If you give the GPT-4V the crop image already, all right, not even giving the target object, right? You're just giving the crop image. We can already get the answer. Look at this. What's the instrument held by an ape? Over here is brass wind instrument for the beginning. You cannot find the guitar. But once we crop into this part here, which is 2 iterations of the search model, you can see that it's a toy guitar. So they got it right. So GPT-4V, if you supplement it with some form of cropping, and then like, how do you guide GPT-4V into getting the right image? You might use the heatmap, the segment anything model heatmap, and do it. So that, I think that is great. Yep. So hold on, did I pause my screen share? Hi, can you see my screen share? Okay, let me see what's happening. Okay. All right, can you see my screen share now? Yeah, okay, I think I think it's visible. So one thing for this V-star model is that if you use stuff like this, where you make the prompt a bit less specific, you can see that, like, what is the ape holding? In the end, you can't even get the answer correctly from the model. The ape is holding the teddy bear. So it might be that some of their prompts for the V-star paper are engineered such that it can work. Like, for example, what is the instrument held by an ape? It gives some contextual cues about the instrument already. So this is something that I think we need to watch out for, okay, because it may not work that well, right? In comparison, all right, if you use GPT-4V and give it the same, like even for this crop image, all right, it got the wrong localization stuff, all right. But for GPT-4V, all right, what is the ape holding? What we'll get is that you get the correct answer. So in some sense, GPT-4V is actually more generic than the V-star model. So the last thing that they did was some comparison on the COCO 18 dataset. which records how a human gaze fixates on particular parts of the objects. So this is the COCO-18 dataset here for the eye fixations. And they find that if they put in the human fixation as a heat map, which is like where the human normally focus on, I pass it as a heat map, the search length is drastically reduced compared to like depth first search or breadth first search, right? We basically see that there's a performance gain if we use the human heat map, right? And the LM guided visual search using the segment anything heat map achieves a very similar search length, which means that the way that is choosing the quadrants to focus on is very similar to how a human would do it. So I think this is something very cool. You can see in the next image here, like for example, in a room to search for a certain target, right? We can see that the fixation of the mask is correct. For human fixation is a bit more focused, but in general, you can see that the mask over here matches where the human fixations are. Like here, if you want to find the water bottle, you search the table, and human fixations are more focused to a certain like sections of the computer. But in general, it is quite good. Yeah, and I think this is a validation of the method of this, mainly the mask here. This segment anything model mask is great. So you can see here. Yeah, so this is something that is great. Right, so these are the takeaways for today. That the iterative focusing of this context is a useful way to get better answers. By zooming in to the context, we get better and better views, and we can get better and better responses when we zoom in. And if you take in like target objects as well, you can supplement the context. All right, then the next thing is that this V-star benchmark is slightly biased. All right, so I think GPT-4V is still better. All right, and this clip based on visual transformer embeddings is probably not good because it loses a lot of spatial information. We might need other views. So let's just stop in the last 1 to 2 minutes on some questions to ponder. So if you have anything, you can just basically sound out. But I'm just going to go through the questions one by one. So the first one is V-star does iterative search over one frame of image. Okay, how can we do this over multiple frames? Okay, so like video. So this one Richard and I was talking about earlier. And the main thing is, in order to do over multiple frames, we might need some form of like V-star across sequences of image. And you know, one way is to do V-star separately for each image. Okay, or we can convert the sequence of image into a representational space and do V-star on it. So there are multiple ways to do it, and I think both ways have its merits. Like the first one, V-star separately for each image, we can do the image more detailed. But you know, you might need to do many times because there's many images. If you convert it into one common representation space, like this whole video, you can take the differences of what happens and map it. Like you can then basically get the differences between the two images better. So I think maybe a more practical way is perhaps this one because it's less lossy, because this method is less lossy, and then you can then combine the predictions of multiple image frames together into one later. Okay, so the next question is, how can we use this recursive splitting strategy of V-star to enhance React-based models? So I've been thinking about this. Actually, this is actually one of the interesting things I have. For each React decision or action, you can use a V-star strategy of dividing the input, dividing the action space until you can reach a decisive threshold to do action. So instead of doing it on the entire action space, we can split into subparts one by one. And you know, you can provide contextual cues to interpret the observation from environment in a specific way. So we can implement the V-star in the React method at each action space and each observation space for each step. You can get more and more detailed observations and more detailed actions so that we can do a hierarchical action from the top to the bottom. Yeah, I think this is something similar to the generative agents paper, generative agents interactive simulacra of human behavior. So this paper with the sandbox of 25 agents, they also have a hierarchical action from the top, like which house do I want to go to? Then after you choose the house, then which room do I want to go to? And in the room, what activity do I want to do in the room? All right, then which object do I want to interact with in the room? That kind of thing. So from the top to bottom, general to specific action selection is something like what VStar is doing. Okay, and we can perhaps integrate it with the React-based methods. So this is something to think about. All right, can the recursive search modify the input modality as well by moving to a different abstraction space? I think yes. Okay, right now we are only limited. Right now, VStar is only limited to modifying image interpretation. Okay, so if we have better context hints, we can modify other domains. And likewise, other domains can influence image domains. Yeah, so I would say that cross-modality influence based on a recursive algorithm, image, text, maybe voice, and so on. This will be the future. So we can recursively update our context based on all the inputs together, and based on this updated context, we can interpret each of these input modalities separately, right? Also, another thing is instead of just doing pixel level or patch level, like what the vision transformer embeddings are doing, we can perhaps do like pixel level, object level, scene level kind of interpretations, and this will greatly help to improve the kind of stuff we can extract out from the image. So I think that's something that we can take into account when we do like image interpretation. We can have more than one modality of interpretation. All right, the last question. Why not just start with input images at various scales abstraction spaces? Like, can we not do the V-star search algorithm recursively? Can we just give it all at one go? The answer is probably yes. You can do it. Probably yes with enough compute. Okay, but right now with not enough compute, we probably want to do some form of filtering so that we narrow down the search space. Okay, and yeah, one way of improving this is like if your VIT encoder can take into account multiple scales, take in patches of multiple scales, better spatial information, you might not need V-star. So that's the kind of thing that I think in the future, once we get the encoder better for images, this V-star search algorithm may not be needed anymore. But for now, I think it's a great addition to help improve the vision transformer embeddings. Okay, so that's more or less what I have for today. Do you have any other questions or any other things to talk about? Okay, if not, yeah, thanks for coming, and yeah, I'll see you next time. Okay, so this is the main algorithm again. I'm going back here again. So using a visual search model to improve getting more and more specific stuff, like the target objects, and feeding this specific stuff to the language model. That is a key takeaway for today's paper, and I think this is really something very interesting. I look forward to like more kind of breakthroughs in this image processing modality. All right, that's all for today, and see ya.